Alright, Advent of Code, Day 16. Yet another grid, and this is actually going to be pathfinding, finally. Okay, east, okay. Um, east, yeah, okay, so then, yeah, we'll just do that. Neighbor function, so, or, um, and then the turns should be those two, right? Yeah, that sounds right. I'll give it a shot. It didn't. Um, don't do that. Not the right answer. Okay, fine. 36 steps forward. And east is this way. One turn, two, three, four, five, six, seven. Okay. What did I do wrong here? I think those are right. Yeah, these are right. So this should be 1,000. Oh, right. 2,000. That's not right. Right. Um. Oh, yeah, my start state's wrong here. That's dumb. Um, that is correct. Okay. Yeah, slow. But, okay, first off, that was really dumb. Part of at least one of the. Oh, okay. Man, okay. I don't have this. Okay. Mm-hmm. That's not the right one. Pretty sure I don't. Or that's. So I care about the paths here, which is annoying. Um, how many steps would this take? Quite a lot. Okay. Second example. $64. So that's a check. Okay. Wait, that's all right. That's what that was supposed to be. Okay. Oh, because I need to then call this. Yeah, I was afraid of that. Oh. Um. Actually, there's two issues. I almost feel like a DP approach is smart here. Um. Yeah, I don't want you. Yeah. Um. Actually, not that. Yeah. So it's still gonna be terrible, but. Mhm. Mm. Are you still zero? Okay. I'm definitely going slow. Oh. Okay, now you're actually checking. 64? Okay, good. I was a little afraid of that. Um, but, okay. I was hoping to do better with a pathfinding, but at least I didn't take forever. No, what was it? 2022, day 16, if I remember correctly. I was just very glad to even be done with it. Now, this problem was nowhere near as bad, and actually, humorously enough, is also day 16. Let me double check. Yeah, this had the valves and the elephants. Yeah, that one I was glad to be done with. Um, yeah, little disappointed in part one. I had that silly, silly bug where I had everything right except for my start state. My start state, I was pointing south for some reason. Because in my grid parsing, north is y -1, and south is y +1. So that cost me an unfortunate amount of time. 638. Yeah, I mean, we all know why those are so quick. How much did I miss part two by? 1347. Oh, wow. Nearly 3 minutes again. It's 2 days in a row with nearly 3 minutes. Anyway, yeah, my part two solution is definitely not super fast. The functools.cache probably will make it run faster. Let's make sure it's. Oh, that's interesting. Adding functools.cache makes it exceed the maximum recursion depth. Huh. That's really interesting. I would have expected it to actually optimize it. Anyway, I'm getting sidetracked. Let's talk about the problem. I can go and optimize this mess later. Yeah, so we've got a grid here, we've got a start position, we've got an end position, and we just need to find the quickest way to get from the start to the end. Uh, it is being a little tricky by saying, hey, you can. It takes 1 point to move forward, but a full 1,000 points to turn clockwise or counterclockwise. Thankfully, I actually have a pretty robust Dijkstra shortest path finding algorithm implemented in my library, even taking into account fuzzy end states, where in this case the graph state is both where you are in this grid and where you're facing. Since I don't care which direction I'm facing when I hit the end, I can just check the coordinate. So I've got an end function. And the other really nice thing that I really like in my library is this make lazy graph, where all I have to do is actually define a neighbor function, and I can lazily generate which other states are in the graph. Now, in this case, this is a finite graph. You could go and generate the full graph, just every single state, every coordinate. just upfront generate the whole graph. Um, but I do like this because I like being able to just think of the neighbor function in and of itself in a more pure functional standpoint. In yeah, in this case, it's maybe a little overkill, but we've sometimes gotten grids where we get just infinite grids, and this is really handy. So yeah, all I had to do was define this neighbor function, which uh, we really have only two modes. We've got moving forward at a cost of 1, or turning left to right at a cost of 1,000. Uh, so yeah, with that neighbor function, with my parsed grid, we've seen my fixed grid library before, and with the start and end points, all at that point it's just a matter of calling my Dijkstra length function, and we get the answer. Yeah, and I wasted time because I just had the wrong start direction. I don't know why I had it pointing south. That was really silly. Um, Actually, one other thing that my tooling has is records of when when answers were submitted. So let's see. So for part one, I submitted first at 3:26 and then 6:38. So I wasted actually just over 3 minutes. If I had not had that bug, I would have had part two because we already saw part two. I missed the leaderboard by just under 3 minutes, so that is disappointing. But that's how it goes. Yeah, and then in part two, we are then counting how many tiles can be on the shortest path, which I am sure there's a dynamic programming way to do this better. I didn't want to think through that, so I just really copied the part one solution to get the best distance, and then went with a really, really crude recursive function, which just searches again, and then it's got some early return conditions. If we see that the cost we've hit is greater than the best distance, or rather the distance we're targeting, then clearly this subpath is not going to be it's not going to be the best path. If we have seen this before and we've seen it at a lower cost, we know that again, whoever's calling us is not on the best path. Um, Otherwise, we just need to check, okay, are we the end state? If we're at the end state, our cost better be the best path, in which case we can record this cell is on the best path and return true. Otherwise, we'll just check all our neighbors and recursively check, hey, are you actually part of the best path? Then at the end, we'll have our set of all the tiles that are on the best path and be done with it. This does, it is not fast. It's taking what? 5 seconds? Or 3, 4, 5, 6, 7, maybe a little longer. We'll get the answer eventually. There we go. It's like, what, 10, 12 seconds? This is terrible. I'm sure I can also keep track of a dictionary of is a state and cost actually part of the path. That's what I was trying to do with functools.cache. I'm not entirely sure why that caused us to exceed the recursion. Actually, that might cause us to exceed the recursion because I think this is then going to cause us every single call is then going to be going through 2 layers. So actually, our stack depth is going to increase twice as fast. That's probably why. Um, I I do wish I remembered how to ramp up the recursion depth. I know a number of other people set it to like 100,000 or something crazy like that in their templates. I don't do that. I probably should consider that. Just so that when I'm abusing recursion, I can at least keep recursing further. Anyway, yeah. I think that's about all I have to say and talk about for this solution. Yeah, I was really eagerly awaiting a pathfinding problem. I was really hoping that when one came up, that would finally be my first leaderboard this year. But oh well, I've got 9 days left. I can hopefully get a leaderboard at some point. It's definitely been a lot more challenging this year than previous years. But we'll see you tomorrow and the rest of the event. So that's all I've got.